Hi. All right. Today's lesson is about logarithmic functions. So by the end, you should be able to explain what the concept of a logarithm is. We want to be able to rewrite exponential expressions as logarithmic expressions and go the other way with that. And then we also want to look at how to use the calculators to evaluate logarithms. You will need a scientific calculator for this. Whether it's the graphing calculators from the classroom or just a cheap $10, $20 calculator from Walmart, as long as it's a scientific one and has logarithms on it. All right. Plain and simply, logarithms are the inverses of exponentials, which means they undo what exponentials did. Remember, an exponential, the x is in the exponent, so that means that there was constant multiplication. So if you did 2 to the third power, 2 times 2 times 2, you get 8. Well, logarithm reverses that. It asks, all right, if you're taking 2 to some power and you get 8, what exponent did you need? So in that case, it would have been 3. So since they're inverses, this is the different ways to write them. Here's your exponential. Y equals something to the x power. Logarithm reverses it. Log. Then down here, now this b is written down in small. It's in subscript. And what that tells you is which base you were starting with. So you're taking log of whatever base of the number that was your end result, and it tells you what the exponent was. So this right here is one of the most important ideas of the chapter. The fact that an exponential and a logarithm are just inverses, and you can rewrite one as the other as long as you remember where all your different pieces are. So when you're doing that, just remember the base of the exponential and the base of the logarithm have to be the same. The exponent from the exponential is the value of the log. All right, so 25 equals 5x, or 5 to the second power. I'm going to write that as a logarithm. So log, the base of the exponent, switch color here with that, becomes the base of the logarithm. We're taking the log of the number we had. And the exponent is what it equals in the end. So we'll draw purple. So this one, 3 to the 6th power equals 729. The log, base 3 of 729 equaled the exponent of 6. Now we're going to switch that around. Log base 1/2 of 1/8 equals 3. Meant if you take 1/2 to the third power, remember that is the exponent, equals 1/8. One more. Log base 10 of 1 equals 0. The base is 10, so the base is 10. The log equals the exponent equals 1. Okay, then a whole bunch of your homework is going to be just practicing that skill back and forth, taking one, writing it in terms of the other. We're going to use this in a section or two when we talk about how to solve exponential and logarithmic equations. Okay? All right, next thing we need to look at really quick is just a brief definition. A common log is base 10. Those are written without the base a lot of times. So if you just see log y or log any number, they're saying it's base 10. That log appears on most scientific calculators. It's only been within the last few years where calculators have been made to do logs of any base. Okay, so before, most calculators are still just base 10 logs, common logs. So because the calculators can only deal with that, we need to be able to use some way of doing all logs using base 10 logs, okay? So many calculators can do common logs directly. And because of the exponent rules, what happens is, whatever log you want to do, you can use it in any base by this formula. Alright, so you want to do the log base b of m. Let's say your calculator only has common logs. So you do the log base 10 of m divided by the log base c of b, where b was the old base, the one you're actually interested in. Okay? So let's do a couple examples here. Now, in order to do these examples, you will need a calculator. If you're using like the TI Inspires in the classroom, and you do a logarithm on that, it will automatically set up where you can add the base and the number you're taking the log of, and that'll give you your answer immediately. Okay? But now if you're at home and don't have a calculator that does that, what you would need to do is do the log of 16 divided by the log of 8. And what you would get, I have my calculator to sit here in my lap, is 4/3. Depending on your calculator, that may come out as 1.3 repeating. Same thing. Alright, the next one, that's supposed to read the log of base 64 of 1/32. And we get negative 5/6. So be sure you're getting these things. If you have a calculator at home, I would definitely suggest working these, making sure you get the numbers I get. And again, if you have a calculator that doesn't let you just type in whatever base you want, you have to use common logs. This would be log 27 divided by log 9. And you get 3 halves. And lastly, I have a common log of 100. Don't even need a calculator for this. Think about what logarithm means. What power do I need to take 10 to give me 100? Well, 100 is 10 squared, so the exponent was 2. That's how logarithm works. So, in chemistry, like it says, the acidity is measured in pH. And I don't know why this broke like this, but it's negative log of H plus. And H plus is the concentration of hydrogen ions. So the pH of lemon juice is 2.3, which means 2.3 equals the negative log of H plus. And we want to know what the concentration of hydrogen ions is in pH. Now the first thing we're going to do is get that negative to the other side. Alright, so it's a log base 10, which means if we rewrite it the other way, we get that the concentration is the same as 10 to the negative 2.3 power, which is about 0.005, or roughly 5 out of every 1,000 particles, molecules, I guess, in whatever we're measuring. Lemon juice is that hydrogen ion. If we do the same thing with the pH of milk, what we wind up with is that the concentration is 10 to the negative 6.6 power. And I'm following all the same steps I did above. What I get then is 6.6 pow. 2.5 times 10 to the negative 7th, which is the same as 1, 2, 3, 4, 5, 6, 7, 8. It's a teeny tiny little bit, which means only 10, 100,000, 10,000, 100,000, million, 10 million. So 25 out of every 100 million particles in milk is a hydrogen ion. That's why it's a weak acid, extremely weak. Another way to look at that is if you divide the concentration in lemon juice by the concentration, 1, 2, 3, 4, 5, 6, in the milk, you get that the lemon juice is 20,000 times stronger of an acid than milk, which is a whole bunch. And we see that one of the things about a logarithm is, because the way exponents work, and logs are exponents, a small change in the value of a log will make a huge change in what we're looking at. So we went from 2.3 to 6.6 on the pH scale, but that's a difference of 20,000 times, a factor of 20,000. So those are hugely different numbers. All right. So the homework for this section, page 441, 1 through 36, and have fun with that.